Welcome to the Explainer. Have you ever wondered how a few lines of text can turn into the physical, thinking brain of your smartphone? Well, today we're diving into Verilog, the language that literally builds the digital world all around us.
Okay, so let's just start with a problem that sounds, well, basically impossible. Inside every single device you own, there's a processor, this tiny, microscopic city of circuits. So how in the world do engineers design something they can't even see and, get this, guarantee it works perfectly the very first time it's made?
The scale we're talking about here is it's staggering. We're not talking thousands or even millions of parts. Modern chips have over 100 billion transistors, and every single one of them has to be in the exact right place, doing the exact right job.
And as you can imagine, the stakes are unbelievably high. Actually making one of these silicon chips is a super expensive, really time-consuming process. You can't just build a prototype, see if it works, and, try again. A single mistake, one tiny error in the design can make the entire batch totally useless. We're talking millions of dollars and months of delays down the drain.
So the solution was a total paradigm shift, a completely different way of thinking. Instead of trying to draw this impossibly complex blueprint by hand, engineers came up with a new method. They started describing the hardware, what it does, how it's built, using a special kind of language.
And that language is called Verilog. It's what's known as a hardware description language, or HDL. Now here's the absolute key difference you have to get. Unlike a language like Python or C++, you're not writing a list of instructions for a computer to follow. You are creating a detailed description of a physical object. This is probably the most critical concept to really wrap your head around. A software program, right, it runs sequentially. It does one thing, then the next, kind of like dominoes falling in a line. But hardware is completely different. It's parallel. Everything exists and is operating all at the same time. When you write in Verilog, you're describing thousands, maybe millions, of little logic gates that are all active, all at once.
So let's take this super simple line of Verilog code. In a normal software language, this would just be a one-time calculation. But in Verilog, this isn't an instruction. No, it describes a permanent physical structure, an AND gate with its inputs physically wired to signals A and B, and its output permanently driving a wire called out. It just exists all the time.
And designers can write this code in two main ways. One way is what's called behavioral style, where you just describe what you want the circuit to do. Think of it like saying, add these two numbers. The other way is structural, which is more like building with Legos. You grab pre-existing components and you describe exactly how you're wiring them all together.
Okay, so this brings us to the most critical part of the whole process. You've got this massive text file describing your chip, but you can't just press run and see what happens. So how do you test it before you commit to that multi-million-dollar manufacturing step?
The answer is something called a test bench. And this is exactly what it sounds like. It's another chunk of Verilog code, but this one is not meant to become hardware. Its only job is to test your design. It acts like a virtual laboratory bench, feeding inputs into your circuit and then checking if the outputs are exactly what you expect them to be.
So then you take this whole setup, your design and your test bench, and you run it through a simulation tool. This is software that reads your hardware description and simulates its physical behavior, literally down to the nanosecond, showing you exactly how the real-life chip would operate. And the output of that simulation looks something like this, a waveform diagram. Designers can see precisely when an input changes, and then, a few nanoseconds later, see how the output reacts. It's so detailed, it even models the tiny physical delay it takes for an electrical signal to actually travel through a logic gate. It's incredible. So here's the crucial takeaway. It's this incredibly powerful loop. You describe the hardware, and then you verify it completely in simulation. You can run millions of test cases, tweak the design, re-verify it, all inside the software world without ever spending a single penny on manufacturing. This right here, this is what makes modern chip design even possible. All right, so let's put it all together now. The entire workflow, from just an idea to a physical chip in your hand, follows these 4 key steps. We've talked about how designers describe their work and then verify it in software. Now we get to the step where the real magic happens. This step is called synthesis. This is where a really powerful piece of software, a synthesizer, reads your high-level description. Remember, something like a sine sum equals x plus y, and it automatically translates it into a detailed blueprint. This blueprint, called a netlist, specifies the exact logic gates needed and every single wire that connects them. So once that gate-level blueprint is finalized and, triple-checked, it gets sent to a specialized manufacturing plant called a foundry, or a fab. And there, through this crazy, complex photochemical process, that digital plan is literally etched onto silicon wafers to create the final physical chip. And the power of this whole describe, verify, synthesize workflow is just its incredible scale. It's used to design pretty much everything, from the CPU that's the brain of your laptop, to the GPU that renders your video games, all the way to the custom system on a chip that runs your entire smartphone. It's all built this way. It is pretty amazing when you just stop and think about it. This entire, vast, complex industry, this creation of microscopic machines that run our world, it all begins with a designer, somewhere, typing lines of descriptive code into a simple text file. And that text file, it ultimately becomes a tangible piece of silicon, a highly complex engine of logic that powers our entire digital reality. The abstract description literally becomes physical.
This whole process, it really raises a fascinating thought. We've figured out a way to translate pure logic, written as language, directly into a complex physical object. It kind of makes you wonder, what's next? What else will we be able to build in the future just by describing it?